a function and an inverse is. However, we now have to talk about when we can do this and when we can't. So obviously we could do it for Celsius and Fahrenheit, but why? And the reason why is because if we have a function, again, that just goes from something to something else, like it takes inputs and gives us outputs, what we want is we want sort of a relationship where there's exactly one input and one output. This sort of is a very, very basic and foundational concept in mathematics, and just as with everything else in mathematics, it has a weird name. However, it is also known by a much easier name, which should be no surprise to anyone, which is 1, 2, 1, literally. Because it takes one input to one output. This seems fairly standard though, so are there examples of functions which are not one-to-one? And yeah, of course there are. So one of them is going to be f of x equals x squared. When we look at the graph of this function, we can see that at -2 and 2, they both output 4. And so we can see that f of -2 equals f of 2, they both equal 4. And so we have, in a sense, this function takes -2 and 2 and gives us 4. Because this is not one-to-one, like we do in fact have 2 only goes to one number, and -2 only goes to one number, but 4 does not come from just one number. So this is not one-to-one. Another way that we can understand this is to say we want to have functions which are invertible, right? That we can reverse the process of or undo whatever the function is doing. And if we look at this, the way to reverse this would be if we had an input of 4 and it gave us outputs of -2 and 2, right? Literally just undoing whatever x squared did. However, now we have one input and 2 outputs. And we actually know this by a different name, which is failing the the vertical line test. Spoiler. It fails the vertical line test because it takes one input and gives us 2 outputs. And on our graph, if we were to sort of ignore this property and just assume the inverse did exist, the inverse would look like this, which again I know because it's symmetric about the line 45 degrees. And so here we can see that at 4, it does indeed cross this at 2 and -2, but because it does it for more than one point, it fails the vertical line test, and so whatever this structure is, it's not a function. And so the inverse of a function must also be a function. Because of this fact, this is impossible, and so we can see that f of x equals x squared is not invertible for a number of reasons. One, we can't reverse it, pretty obvious, and 2, the sort of newer, higher level understanding is because it's not one-to-one. So, is there a nice way we can tell when something is one-to-one? And yes, there are going to be 2 ways. One is fairly easy, but a little bit harder to understand, and the other is super easy, but not always applicable, because why would it be easy? So we can say one-to-one if, and this is the formal definition, it says if f of x1 equals f of x2, this implies, which is what this arrow means, that x1 equals x2. So x1 and x2 are inputs, and if their outputs are equal, the output of x1 is f of x1, and the output of x2 is f of x2, because we're not specifying what f is. If the outputs are equal, but the inputs are not, then it is not one-to-one because it fails this implication. So, going back to x squared, we can see that -2 squared equals 2 squared, right? They both equal 4, but -2 does not equal 2. So, it satisfies the first part, but negates the second, and so it's not true. So we can see that x squared is not 1 to 1. And we can see that in a number of ways. One was doing it sort of logically before. This is doing it algebraically by using the definition. Another way to tell when something is 1 to 1 beyond the formal definition is to get back to what I accidentally slipped up as a spoiler, which is the horizontal line test. The vertical line test determines if one, or I should say, if an input has more than one output. So this sort of tackles half of being 1 to 1, which is that one thing goes to one thing, right? So the vertical line test, if a function passes the vertical line test, that means that every input has exactly one output, which is good, but not enough, because x squared also passes the vertical line test, but we know it's not 1 to 1. The missing property is we need the horizontal line test. I don't even know if I spelled that right. Horizontal line test. This determines if an output has multiple inputs. And so the way we can think about this is if we take some function, something weird like this, and we say, yep, this is actually a function because it passes the vertical line test. I can take my pen and pen it across, and it only ever intersects it at one point. However, I can take, let's say, this value, like let's say that's 1, and I can say, is there only one input that gives me that output? And the answer is demonstrably no, because in fact, there are going to be 5 different points of this function, which all output 1. So, while one input goes to one output does not come from one input. And so this is not 1 to 1. And the way we found that is by drawing a horizontal line. So, just as with the vertical line test, we have the horizontal line test, which gives us sort of the other half of being 1 to 1. So, we can use the formal definition of 1 to 1 to find out if a function is invertible, and we can also use the vertical / horizontal line test. And the sort of punchline of this is because functions which are invertible are exactly of the type where one input goes to one output and one output comes from one input. That way we can reverse them and we preserve that relationship. Because invertible functions are 1 to 1, we can now check if a function is invertible by checking if it is 1 to 1. So we can now say 1 to 1 implies invertible. In fact, that's it for the classification. It turns out that this implication goes the other way as well. So if you are invertible, then you must be 1 to 1, which is kind of how we got there logically. But being 1 to 1 also implies that you are invertible. So either one gives you the other. With this, we can now try a couple of examples to see if we can tell what things are and are not 1 to 1. So we just checked it for x squared, and we found that it passes the vertical line test, but it fails the horizontal line test, and because it has to, then it is not 1 to 1 by the definition. So let's try the 4 examples that I have in the notes, with the first one being a graph of f of x equals the floor function of x. This one is our familiar step function where we get a staircase structure out of this. And yes, people can see that. So now we can use the definition of 1 to 1 to check if this is invertible. To do that, we can say, we can just check. the floor function of 2, I know, is going to be equal to the floor function of 2.5, because these both equal 2. This is just what the floor function does. However, 2 is not the same as 2.5. And so we can tell that this is going to fail to be one-to-one because it doesn't satisfy the definition. And we can also see that while it passes the vertical line test, it fails the horizontal line test because it's going to intersect this little segment not just at one point, not just at 2 points, but in fact everywhere along this segment, which is going to be infinitely many points, which it's enough to say is just more than 1. So it fails the horizontal line test, and likewise it fails to be one-to-one. Again, this is because of our correspondence, which goes both ways. So the answer to that example is no, it is not invertible because it is not one-to-one. The next one is a graph which looks like that, which is f of x equals x cubed. And this one, we can again apply the same reasoning to see if it is one-to-one and thus invertible or not. So first, let's check, does it pass the vertical or horizontal, or not or, the vertical and horizontal line test. And for that we can, again, use my pen to say as we pan a vertical line across this, it only ever intersects it at one point, so it's good for vertical. And likewise, if I pan a horizontal line across this, we see that it only ever intersects a horizontal line at one point. So it passes the vertical and horizontal line test and thus should be one-to-one and thus invertible. We can also check if x1 cubed equals x2 cubed, does this imply that x1 equals x2? And if we think back to x squared and why it failed, that's because negative numbers, when you square them, become positive, and positive numbers squared are positive. So they sort of both output into the same set. However, if x1 is negative, then x1 cubed is effectively negative times negative times negative, and we know that two negatives combined give us positive, and then the third negative is going to give us negative. So if x1 is negative, then x1 cubed is negative. And likewise, if x1 is positive, we can do the same thing. Positive times positive is still positive. So we see that this, the two outputs are going to be equal only if x1 and x2 have the same sign, being positive or negative. And then, if they have exactly the same sign and they output to the same number, then they have to be the same number. So this implies x1 equals x2. And so their outputs being equal, implying their inputs are equal, is the definition of being one-to-one. And so we can say that this one does work. And we get that x cubed is in fact one-to-one, and so is in fact invertible. Next one is going to be the graph of f of x equals 1 over x, and this looks something like that and that, not drawn to scale. And we say, all right, is this one one-to-one? Because we're wondering if it is invertible. And the answer is, well, let's check the vertical line test. Vertical line only intersects at one point, only at one point, only at one point. As it gets closer and closer to the y-axis, it still only ever intersects at one point. And at the y-axis, it doesn't intersect at anywhere because that would be equaling positive or negative infinity, which aren't numbers. So this function gets sort of arbitrarily close to infinity, but can never actually be infinity, Likewise for negative infinity, and so a vertical line still only intersects at one point throughout this entire thing. We can also check the horizontal line test, and we see 1 point, 1 point, 1 point, and for exactly the same reasoning as a vertical line, it gets closer and closer to having these two trends be on the same horizontal line, but they never will because that would involve infinities, which we know aren't numbers. So this does pass the vertical and does pass the horizontal line tests, and so it should be 1 to 1. Let's check again using the definition. So if 1 over x1 equals 1 over x2, being the outputs for x1 and x2, then we can multiply everything by x1 over x2 and by, hang on, alright, I probably shouldn't skip steps. So first let's just do multiply everything by x2. This is going to give us x2 over x1 equals 1 because the x2's cancel. And then we can multiply everything by x1 where we get x2 equals x1 because the x1's cancel. This, however, is exactly what we wanted to find, which is that if their inputs are equal, or sorry, if their outputs are equal, then their inputs are equal. And so just as we found with the horizontal and vertical line tests, 1 over x is indeed a one-to-one function, and so is invertible. The last one, the last example that I'm going to go over today, for this video lecture anyway, is going to be letter D in the notes, and this one is similar to the graph of x cubed, but it goes like that, with a gap right there in the function. And so we can ask, does this still pass the vertical and horizontal line tests? And for vertical, it's pretty clear that it still does, but for horizontal, now we can pan this across and we only get 1 point of intersection until we reach this gap where we now have no points of intersection. Everywhere in this range, a horizontal line is going to intersect our graph nowhere. And so